Good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. My name is Francesco Petruccione. I'm the director of NITheCS. And this afternoon, it's a great pleasure to welcome Professor Eckhard Platen. Professor Platen is here for a workshop attended by, I think, by most of you in this audience, so I don't have to remind you of that. Professor Platen is famous to me because of his book on numerical methods for stochastic differential equations, yeah, which I had the pleasure to study in. I think there is a little bit of echo. It might be the microphone here. Yeah, okay. No. Switch it. I think now it's off. Yeah. So he's famous for this famous book, yeah. So and I just checked how many citations it has, and it has a lot of citations, which is probably not typical for a mathematics book. Yeah? So well done for that. Yeah. At the moment, he's emeritus professor for quantitative finance at the University of Technology in Sydney, and previously was at the Weierstrass Institute of the Academy of Sciences in Berlin, and the head of the Center for Financial Mathematics at the Institute of Advanced Study of the Australian National University. Yeah? And today he will share with us some really interesting new developments, yeah? That start getting interest to you if you are approaching 60 plus. Maybe it's too late.
It's too late.
But who knows? Yeah, but maybe we can save the next generation. Yeah? So Professor Platen, thank you very much for agreeing to give a talk, and we're very much looking forward to your presentation. Thank you.
Thank you very much, Francesco. Okay, some of us have met this morning, but welcome again. But now I'm presenting the ideas a bit more public in a way that one can see really how it can be changed. Not very fast, but over a longer time, significantly how someone can retire. I'm writing a book on it. Actually, its dedication is for my grandchildren, so that they get hopefully much more out of their contribution to their pension plans than it's now possible. But you kindly reminded me that I wrote this book on numerical methods for stochastic differential equations. So it was the first half of my academic life, I would say. And yes, I'm very proud of it. It was very successful. But I made a decision in around 1990 when this book was almost finished. I said to myself, okay, done, go to next something else. And it was obvious where I'm going because these stochastic differential equations, these are the models for the securities in the financial markets. It's ideal and it was hot. The derivative market was booming. And I immediately went into some questions there, which was option pricing, value options. And yes, I got an invitation to spend a year or so at the Institute of Advanced Studies in Canberra for the numerical methods, not for any finance. But I came there and gave talks in Sydney, Bankers Trust, at that time leading investment bank, derivatives bank. They saw me talking and say, Eckhard, we can't believe what you are talking here. But it's just, no one can do that. I said, okay, give me a chance. I got a chance. We gave some examples for barrier options, which were difficult to price. And they saw the pretty much correct prices now and traded it, and it worked out. And at that time, just a hedge over a few months. It was perfect. They were excited. And I got first very good consulting money, but later I said, it's enough, guys. You have $10 million bonus at the end of the year. I want a Center for Financial Mathematics at the Fine Institute of Advanced Studies. And they did that. It was a fantastic time. I worked with them. And then I got critical. This question was, which was on my mind, there's this S&P 500, the US stock index. And they write options or not. We did it, but short term. I say, what is when I do a long term one, 35, 40 years for a pension or for a variable annuity? I actually had a nice dinner with the head once from New York who flew in, and I thought, ask him, how would you price this put option? What would be your price? He looked at me, said, no, you have the technology here. It's financial mathematics. It's fine. I said, okay, every theory has its limits. And I feel it's overpriced, clearly overpriced. And we discussed, and then I gave up because he said, Eckhard, we are the market. And then it was over, the discussion, and I never touched it. But still, a few months later, I had a phone conversation, and he said, Eckhard, I want you in New York or London, you can choose, and another quant group, and we need this. And I said, no, not coming. Because I had this idea, something is there in the mathematics that we don't know. And banking is coming and going, and it did. So I was pretty lucky, just follow it up. So this benchmark approach, which I'm using here, grew out of that. But it took a long time. More than 25 years. Step by step, I got more, and the colleagues who came out all these conferences over this year now, how it evolved. So, but today, I like to talk about how could it be useful for pensions, for long-term payouts. And in principle, it's so. The ideal thing would be if people wouldn't, of course, not retire poor, and the average person, shouldn't be really fully responsible for the investments to make. How should he or she know how a defined contribution pension, how she should manage the money, even with the help of some financial advisor? It needs a lot of education, and you can see this when I show you. So, but the easiest thing would be naturally to have an annuity, also some payment stream, say from the date of your retirement onwards, every beginning of a month you get a certain amount, like your salary, for a period, say, of 12 years or something. And yes, but mainstream finance literature says they are expensive, and they are actually expensive. In Australia, almost no annuities are really sold, and they are too expensive. But why? There are different opinions. Still, they are expensive. There's a deep reason for it. But it would be great if an annuity type instrument would be available to everyone for a cheap price or for the best price. Our classical finance says you can't do much. This is how it is. You have to invest in very much fixed income and roll it over. And when it comes, then it comes. If the interest rates are high, it's fine. If they are low, then it's a problem. And if they're negative, there's definitely a problem. So the main question is then, can one generate from pension contributions higher riskless pension payouts than currently produced? Can one do this? And I say, yes. Those who were this morning in the lectures saw where the theory is. It's clear, it's mathematical. It's a benchmark approach with now some new developments, which will make it really very interesting and ready for application. So here, let's look at the US dollar savings account, which where you can see, I don't know whether I can do here something with a cursor. Yes, I can. Where you can see, for instance, this period where we had pretty much zero interest rate. But on the other hand, it made about from 1 unit of the savings account became pretty much to 12 or so dollars. It's quite significant. This is a kind of effect we have, which is in the pension industry, life insurance industry now more or less by the actuaries employed And this is how one builds and how one calculates then annuities. But we have the stock market. And of course, the stock market is growing much faster than the fixed income, also the savings account. And can we harvest this in some way? Okay, sure, we could go into it and then invest everything into such a stock. But what happens then is like here, look, the great financial crisis, you go from almost 5,000 down to almost 2,000, 41% drawdown. It's terrible if you really retire here in 2008. Yeah? You lost it. So this is not necessary and not desirable. Can we avoid this? How we can do this? Yes, one can do it. So in classical finance, or now how it is established, if you want 1 unit of the savings account at your extreme maturity date in 40 years, there's one strategy of doing it, and only one strategy. You invest in the savings account and hold it until the time you need this payment. That's it. The law of one price. Every economic student learns it just in the first lecture. There's no way that you can escape it. The teacher will tell you. And I say, sorry, we can correct this, improve it. So, and if you improve it now, let's take a very simple example. A payment of 1 unit of the savings account at this after 40 years maturity date, and ask the question, how expensive would have been at the time T where we are when we buy it, an inexpensive approximation of this kind of zero coupon bond around, which gives you at the end the zero coupon bond, which is 1 unit of the savings account. How expensive would it be? Is it so that the theory which I have here, what I'm talking about, does something, but it is minor. It's not really, it's a secondary effect also. Let's check this out. And how I have to talk about a formula. I sometimes call it, it's a magic formula. And I found it just by doing mathematics around this thinking, how we can make things more correct. And this formula is here, which is the zero coupon bond price at the small time t for an extreme maturity or for some maturity t, where it pays 1 unit of the savings account. And the price is 1 minus an exponential of minus the stock index, which we saw before, divided by 2 times an exponential of some activity time at the maturity date minus an exponential of the activity time at the time where we are. This is a formula, and it's fantastic once you learn about it. But at that time, I took it just as a result, it's just an expectation on something I had done. Okay, but I used it then in papers, and recently I did some work with Giovanni Barona Adesi in Lugano, where we used this formula, used the S&P 500, and wanted to see how much money can one get out and how much extra money one has to put aside to make sure that 99% of the payouts are really what we want, this 1 unit of the savings account. What we did is we took not the activity time itself, which you can observe, I show it on the next slide. We took the trend line. It is, because this is pretty linear, we took the trend line and just plugged it in here and there in this formula and put it out. This paper appeared last year in the Journal of Pension Economics, and it showed that one needs an extra 6% of your payment at the beginning to be then with your hedge secure that 99% of everything is just paying correctly out what you want. So you need a bit of extra money. But at that time, when we wrote this paper, I didn't know what I learned bit by, almost accident, because I came back to my spreadsheets and did a little bit of my calculations again and checked it. I just plugged in here at this place, not the beginning of this trend line, now really the time which I can see. I can observe that this activity time and made it so. And suddenly, what 6% was in the paper with Giovanni, there's far less than 1% what I needed extra. There's nothing. It's accurate. This formula is working. So surprisingly accurate. Okay, I have to give you a little bit of a background of what is here the mathematics. I talked about this activity time. You can calculate it. You can calculate yourself. Everything what I'm talking about here today, you can go on your spreadsheet and do it. You calculate the quadratic variation of the square root of the stock index. This is nothing else. Just sum up over the discretization points you have the squares of the increments of the square root of this index, these things. And then you get this here in this equation. You don't know this at that moment, but you see already when you have a long time series, this is pretty linear what you get here at this time. So you play with this initial activity time, find the right one which maximizes, say, make it as much as possible a straight line. So you maximize the R square value of this trend line. And then you have your parameters. So you get your trend line, but you see also evolving all the time this activity time. So, okay, that's it, what we need. Here is the graph with the MSCI World Index total return. This blue one is the activity time. Look, in 87, there is a bit of a jump here, and so on. Here, great financial crisis, another one. But the trend line is just going nicely along. So what I'm doing now is we plug in this blue curve as it evolves and try to come then finally there. So here is the price process. At the end, we reach 1 unit of the savings account, but before there are prices. From this magic formula here, there it is. So at the beginning, in this case here, you have still to pay, say, 0.18 unit of the savings account at the beginning, and then you get on here. But think of now that it is discounted by the savings account. So you get, when you start here, for 1 unit of the savings account, which was here $1, you get then $10 to $12. You saw it from the earlier graph. So here's the hedge portfolio. Anyone can do this on the, say, on a spreadsheet also, and in reality, of course. Important is this one. This is the weight with which you invest in this stock index, like the MSCI World Index. Here's the price again. Here's the price again, a strongly nonlinear. It's a very surprising formula, but with magic, I must say so. So you press it in here, you get the new value of your hedge portfolio from the old value by investing with this weight in this stock index. Self-financing, what comes out. Of course, it will be not exactly the theoretical price, because this is discrete in time, but you get here is the weight, and later the value, I show you in a minute. But the weight is so, when we have a long time to maturity, then we are almost fully invested in this stock index. As we come closer to maturity, we get more and more divested and get it all wealth into the savings account. What we want at retirement, we want to be in this riskless security. But this here, ups and downs are very important. You have to follow them exactly, otherwise it doesn't work. But there is a bit of an intuition. Even if I ask finance professors, mainstream finance professors, how have you invested? They say, oh, no, yeah, in stocks and real estate. And yeah, now at the retirement, I'm mostly in fixed income. I say, oh, yes, that is the general financial planning strategy. And then I should continue, but I don't do it. I should say to the finance professor, but it is not the risk neutral strategy. You should have been in the savings account all the time. Okay? So there's a contradiction already in the real world. Financial planning is intuitively doing something. What we are doing here is we make that rigorous. and not only rigorous, fully optimal. So the striking thing now is, and this is new, and this is why I'm so convinced now and have to do something about it, is that the error, the hedge error, the mistakes from this discrete hedging, what you do, in the model you use here behind, which I haven't mentioned so far, is so small that if I would put the graphs of this hedge portfolio and the theoretical price one over the other, you wouldn't see any difference. You see only one line. And here is the hedge error at, you'll see, 1987, there was the stock market crash, also the October. This is a big error. This error is small. Look at this. Altogether, we are below 0.02% of 1 unit of the savings account. This is nothing. Yeah, this is nothing. And so this is pretty much not the source of any worry in when you want to apply this whole methodology. So why is it working? Because I wouldn't invest into something where someone tells me something like I'm here talking and hand waving and so on. There must be a sound theory. We must understand why is it so. And then we can trust that it will, the next 50, 100 years when we do this kind of investment. Yeah. So, and this comes now where I had this benchmark approach developed over the years, starting from this put option question which I had in my head, but I understood then pretty soon the gross optimal portfolio, also the portfolio that maximizes the log utility, expected log utility for those who come from this corner, but you take the logarithm of the portfolio and its trend, its drift, that's more or less what you maximize. And this plays an important role, and I called it then benchmark, and so it became benchmark approach. And actually, it's really the benchmark very much also in fund management terms, where such a very well diversified stock portfolio plays a central role. So over the years, I developed the theory. So in 2002, I talked about some kind of arbitrage in a classical sense that is possible. And here I have a book with David Heath on the benchmark approach to quantitative finance, and then the recent results, which I'm putting into this talk here also. So the real progress, which is rounding it up for me, at least at the moment, is coming close to physics. Like Francesco has in quantum physics, a lot to do with the NITheCS theorems. The mathematicians don't own it. I didn't see that ever in my education. When I went to university, it didn't come up. It was group theory, but not this NITheCS theorem. But in physics and other areas of human knowledge, the NITheCS theorems have proven to give us access to the laws of nature. What are they doing? Roughly speaking, you have to describe your complex dynamical system, whether stochastic or not. You describe it with the help of partial differential equations, system of partial differential equations. Okay, it has to be done in the right way, otherwise it becomes a bit complicated. Okay, once you have this, then you decide what is the most important driver in this complex system, which makes it moving somewhere, hopefully to some equilibrium or something like that. And this gives you then a Lagrangian. And this Lagrangian you minimize, maximize, depending on how it is written. And a solution of a PDE comes out, which is then the ideal optimal dynamics. Once you have this, then there's coming more. And NITheCS theorems, Noether realized that Lie group symmetries in these PDEs that come out generate conservation laws. So what is a Lie group symmetry? It's nothing else than an operator on a solution of a partial differential equation which brings this solution into another solution which is of the same type. And this is very special. We have learned, and Noether found it out, that this is what is very crucial to get the laws of nature. Actually, she did it in Göttingen, in the group of David Hilderer, and it all happened this way, that Albert Einstein came to Göttingen, talked about relativity theory. David Hilderer said, "This is not really perfect, Albert, something. Let's think about it." So he told Noether, "Look at this with your expertise in harmonic analysis, and there must be something." And she looked at it, came back, and said, "I understand not only what Albert Einstein is doing here, no, in thermodynamics, in Newtonian mechanics, and in other areas where laws of physics and chemistry and other have been found, they all can be formulated in the following way. You write it down as PDEs, you find a Lagrangian, you maximize or minimize it, and then you check whether you find Lie group symmetries, and when you have them, then you solve them, and you look at it, and bang, you have your conservation law. That's it." So what I was thinking, in finance, we don't have that. Also in economics, we don't have that. Why don't we have that? Let me try. I'm now not forced anymore to publicize or to publish. No dean is coming and say, "Eckhard, how many papers did you write? This guy brought 15, and you have 2. And they were even written a year before." Oh, no. So I spent my time on this kind of idea. If I can make it in the rest of my academic life, just get this question in some way solved, then let me do that. So I invested. The key thing was now, with the ideas and the knowledge of the Noether theorems, to find the mathematical principles that would do the job, to give me the undisturbed, most undisturbed solution dynamics of the market. So 2 principles finally came up this way, but it was a difficult, not so easy process. The first is that this gross optimal portfolio, the best performing portfolio in the long-term best performing portfolio, is that this exists, that doesn't explode. This is a trivial assumption, because if it would not exist, or if it would explode, it would mean someone can make in finite time infinite amount of money out of a little bit of money or even nothing. And I need PDEs, so I have to put in something which does it, and it's clear. I've all the time worked on a stochastic differential equation and diffusion processes, so there has to be a diffusion because its transition probability density is the Fokker-Planck equation, so I have PDEs there. So then the second step, this wasn't so easy. I had a long time to search, and I was thinking on entropy and entropy of value and all these things, but very easy at the end once you know it. The market, and you would all agree, the market is a communication system. Information is revealed with every trade. The more trades you have, the more communication is going on. And it is not the monetary value really, because the central bank can print money, and then suddenly there's some inflation, or can take money out of the system. So the money itself is not, no, that is the information that counts. The information about that. So, and which information? Of course, the information about the dynamics, these PDEs will describe it, and the other is price. And here it's enough to look at the short-term prices, which are so that you consider it as being riskless if everything is like the savings account, and more risky if not, so pretty much the risk-neutral prices would be here. All the mathematicians here, Karatzis and Kadaras, have just shown then that this first principle, the existence of the gross optimal portfolio, is nothing else than a no arbitrage condition, but a very special one, and they know unbounded profit with boundless risk condition. Shannon, this comes in with the second principle. The most unpredictable market dynamics come out when we minimize this information, what I was talking about. And also, since we use for the pricing measure, we will minimize the so-called market prices of risk, the risk premium, also what you get when you go for risk. You get more when you go for high risk and less when you get for low risk. And then NITheCS result says, okay, finally, if I would find it, then Lie groups would create the conservation laws, which I may have. So the benchmark approach is purely mathematical. And the benchmark itself, which later comes in pricing, is nothing else than a very well diversified portfolio of, say, stocks. But the better one, and the one what we need, is another gross optimal portfolio just for the stocks, which emerge by buying low and selling high certain securities. It's not just a buy and hold strategies. So, and out of these principles, then pretty much everything falls, the market dynamics and so many other things. So roughly speaking, the risk management, which is now the paradigm and taught everywhere in most of the papers, is so it evolves around the savings account. Where what I am doing here, it will evolve and is evolving around the benchmark. Since it is growing faster, you can get, in principle, more out after a long time. And short time differences are not very big. So the gross optimal portfolio exists. This was the first principle. It gives the so-called real-world pricing formula. And this is pretty interesting. One can price using just the probabilities you know. It's actually very interesting for insurance. But you need as numeraire, as denominator, the best performing portfolio of everything of the entire market. And this gives them the minimal possible prices. So here I show you again the known, the discounted MSCI World Index for all the stocks. And do the following. I go for this portfolio, this benchmark, which I want, which I have to create, where some buy and, also not a buy and hold. No, there is a dynamic asset allocation strategy where I try to keep the weights pretty constant. The theory tells me this to do, and I call it the EWI 163 for some technical reasons. But you see the yellow or orange one down there. This is what I had before. This is the MSCI World Index. But by doing this, buying low, selling high, we get a much better performing portfolio. Look at this here. And going on, I can go on. I can now in this graph, I show you what I showed you before, this portfolio, which is actually the gross optimal portfolio of the stocks alone. I add a savings account to the market. I can go short. That means I can borrow stocks and have that then in the savings account. And with this leveraged portfolio, I get this here. And this is actually the portfolio which I really have to use when I want to use the real world probability to get prices out, the minimal possible prices. So this is even more better performance, but now you can see it's enormous, it's volatile. It's very difficult to make it a really tradable security. It's possible, but I wouldn't really focus on it. Here are the logarithms of all these three portfolios, what I said. So this is the discounted by US dollar savings account, discounted MSCI World Index. You see it has about 5% above interest rate. Interest rate in the US about 5% over this period here. And this is the one where I say it's a gross optimal portfolio just for the stocks at about 14% above interest rate. And this is extremely volatile gross optimal portfolio of the entire market, which is going short significantly in the savings account, but gives you almost 24% above interest rate, also 29%. But it's not very useful because you have enormous volatility at some time. So then pricing can be done nicely. That is part of the benchmark approach. And I use the most optimal portfolio of the stocks alone as numeraire. So this is a strictly positive long-only portfolio. And then theory tells us I can use this. And actually, it's the only numeraire as a portfolio, tradable portfolio, I can use as numeraire, as denominator to do my pricing, where the minimal possible prices at the end come out. And then there is a pricing formula, the benchmark neutral pricing formula. And this here is an expectation under this slightly drifted measure, also the benchmark neutral measure. Okay. If you would take the savings account, this is what we are doing at the moment in most applications. If you would take the savings account and go for a long-term time period with extreme maturity, your price in many cases will be much higher than necessary. And this is why I'm thinking we can do a lot here in the pension area. So there's a model, I called it minimal market model in 1997. I had the first idea about it, and it's working extremely well. And luckily, it's exactly the model in some time scale, which comes out of the minimization of the information. So the information efficient dynamics has this as typical dynamics of the stocks. Here a comment, this dynamics which comes out there tells us a story. The story is the following. Capital evolves in a certain dynamics. Think of all the investments as small capital units. Okay. After a short time, some have created new capital units and some lost some or died. So many independent movements. If you have this and look at the entire capital, what you have there, and ask for its dynamics, what comes out is a so-called branching process, also exactly the dynamic which we have, where there is a square root in the diffusion coefficient in the stochastic differential equation. So this is a, I would say, natural dynamics of diversified mass. And it comes out, and I can show you this, and I showed it this morning in a lot of graphs. So we can calculate now the inexpensive zero coupon bond. I have now a derivation for it totally. Exactly under this benchmark neutral pricing, I get exactly this formula, which I had shown you before, which we tested where we worked as an example. So here is now my favorite, latest practical result. The EWI 163, this approximation of the gross optimal portfolio of the stocks only, which rebalances dynamically every day sum. But even with 40 basis point transaction cost, this is this portfolio, what you show there. And then I plug it into the formula, and this gives me now this zero coupon bond, this approximate inexpensive zero coupon bond. So if you have really 52 years, which I have here in my data, all the data, and then you get, let me see the number. Yes, you have just to pay 0.016 units of the savings account at the beginning when you set it up to get at the end 1 unit of the savings account. And this 1 unit of the savings account are, when you had it at the beginning, as $1 as a savings account unit is even at least $10 or $12. So it's quite a lot what comes out here. It's stunning in a way, and but you know, the hedge has to be really, really done the way. So I'm coming to more and more to the end of this talk. My dream would be also for South Africa, but in particular where it is really needed, instrument which is traded on the market. Anyone could go there and buy it, which I call here term annuity bond. It's of course just an example. There may be other things, but I could imagine it. And this would pay at, say, maybe your retirement date, starting every month in amount, say 1 unit of the savings account. That will be the standard thing. And these payments every month go on until a later date when it stops. So let's say for 12 years we have this. Every month you get a principal, a pension, a payment in some way. So this payment here, you see, the retirement date would be in 2010. And we stop then 12 years later. 12 years is about, for a male, the average life expectancy after retirement. Yeah? So that's roughly it. And that's so simple. This is the price of it, the least expensive price. So let's just go for the decumulation phase. 2010 is here the time when the payment stream starts. Every month you get some payment. Of course, it decreases pretty much almost linearly. You cannot see any real non-linearity here. But this is the accumulation phase. So you go, and anytime you could buy a unit of this, and it gives you then one more unit of the savings account and every month. Okay, so this would be 144 monthly payment of this year. At the beginning, these 144 payments would cost you just this amount of what is here, $3.7 when you think of having here $10 per month paid. So if I would think about grandchildren, I have 7 grandchildren, would have the idea, and I have it. And as soon as it is really live, such an ETF, I will do it. If I would like to have them $10,000 per month paid every month for 12 years after their retirement, I have to come up with $3,700 now to do that. And then this payment stream is there. If I would be going just close before the retirement here and try to do this, I would have to pay 1.4 million. Okay? So here's a lot going on. Of course, the time plays an enormous role, but also the discipline to do exactly this here and the knowledge that the financial market is information efficient enough to support this kind of methodology. So that's very much what I wanted to tell you. I'm absolutely certain, and there's mathematics, I put my own money on it, and there is some there are some companies that I support in a way that do this, and it will be there. There will be ETFs. I wish South Africa there will be benefit. In particular, I like to help these communities, and I'm not so keen to go for any big banks. I would more like to have a cooperative type thing, situation where we pool our money and make sure, according to these principles, that it's all fairly traded. And those who manage this money, okay, they get their very good salaries and so on, but they cannot do much fraud. It will be our money anyway. And anything what is really uncertain and we cannot handle, maybe we all live 20 years longer, then okay, we have to take the money which we have in the pool and live with this, but that's not so bad. We will be okay. But in this way, I think it can be done. And by particularly for the young people, being able now to go on the internet, click an ETF, and the ETF guarantees you that what you pay in is a unit. It's also government supported, that there's nothing going on with all the regulation is doing it. But the person can only get payments at the retirement date, also what we had agreed, and then they get it all every month and cannot take a lump sum or things like that. And this is solving a lot of problems. We don't need to be financial literate. You just do it absolutely clear. You need just to know how much you want. And then as soon as you collect money and you would tell them, the earlier you do it, the more you get out. So don't waste your money in your young years. You don't need this fancy car. Just take what is rolling you and put it into there. It will make at the end so much for you. So this is in principle situation. There is a way of producing higher pension payouts than currently practiced. And this production method is like other high technologies, something, okay, it depends on mathematics, it depends on knowledge, but we do it all the time. We bring some vehicles on the moon, we bring something maybe in future to the Mars, and so on. So we can do this too. It needs a society which just accepts and builds on truth and facts and avoids anything which is then making it all nebulous. And here, this will be a very simple, very clear instrument. You can buy it, you can give it your grandkids as I would like to do it, and you would know how much would you get in case this is all, the whole world is still existing, because these financial markets, when they go, then anyway, they couldn't have done anything anyway. But it will not happen, definitely not. Well, thank you very much for your attention.
Yeah, thank you for a fascinating talk. Thank you. Are there questions for Professor Platen? Please. The microphone is coming. Okay, you're the next one. Please go ahead.
Okay, thank you very much, Prof. Thanks, Prof, for the amazing presentation and a very significant one. I just wanted to understand, there's a question that you said you wanted to tame that had to do with quantitative finance, but actually infusing principles of nature, that is quantum mechanics, into finance. And then you spoke about a certain system that you needed to solve and understand the highly very significant thing in that system, like creating a stochastic system and all of that. So, which is an interesting part that I'm actually interested in as well, trying to fuse quantum computing into finance to solve actually financial market problems as well. So, but then I just actually wanted to understand that what is it that you're aiming to achieve in terms of fusing the quantum, because the quantum physics or quantum computing is quite a broad thing. So what actually are you looking at there in physics to try and take out and to solve in the financial market? And what is it actually in the financial market that you're trying to solve? Is it, because you spoke about derivatives, for instance, are you trying to actually price derivatives by trying to find an alternative way of using quantum physics, or
no?
What is it that you're trying to do?
No, I apologize to you're from physics, I see, and what is here working and what I exploit, and I pointed it out, the general methodology, how we come to the laws of nature, also in quantum physics, in thermodynamics, in Newtonian mechanics. And I cannot go from thermodynamics into finance and say, now it's the cha-cha-cha, we pack this in and it comes out. It is not this way. No. At the beginning, I was a bit thinking like that, but I learned it the hard way. I spent so much time on the wrong track. No, you cannot just come from some area, say physics, in physics, and then do that. You have to go, and it took me, think of it, more than 30 years to work deeply in finance at the absolute frontiers and with all different people and the world leaders in some areas to start to understand what is here the point. Now, and my peers and friends, I had just this morning discussion, say, yeah, information, and it will be bigger, and so on and so on. I'm through this all. Yeah, I'm through this all. This is very important to get rid of certain popular common sense or whatever ideas and learn things what you learned in other areas to apply it just there. Okay, you can try. I tried a lot. But at the end, it turns out it is information what makes it working and puts it together. And information in the information theoretical sense. And it is information about the distribution or density, probability densities of the real world dynamics and the prices, the pricing dynamics. And this discrepancy, the difference between these methods and the self-information of the dynamics, these are the two things which bring practice here, okay, also bring us the dynamics of the market, and I can use it, and then I can build everything on it, derivative prices and so on, like this product, what I was suggesting. Okay?
And Donovan here, just in front.
Thank you. Thank you very much. My question is around the use of Lie groups as a methodology to deal with PDEs. I mean, I think you indicated in terms of getting some conservation laws, but I think what has been a challenge, I think from the paper that I've read, at least, I think is the issue of the interpretation of what they get out of when one uses this Lie groups aspect. I don't know in terms of whether there could be some kind of physical interpretation of the result that one can get when one uses these Lie groups.
Okay. Also it's again, it took me a long time to get to the right description. I use a very particular parameterization of the general continuous market. I have general theorem, which I exploit to reduce the complexity, the structure. So there is certain risk-adjusted return, and there are market prices of risk and things like that. And they're all the same for all the portfolios I have. So I have to use that. So I use this. So, and then I come to the PDEs when it is maximized. And then at that moment, I still don't have the solution. Also not a nice explicit solution. Maybe numerically I could do it. But then it comes here, the Lie groups come in, and I did this work. There's a paper in Journal of Differential Equations with Mark Craddock, where you can see how we do that. I take this square root in the diffusion coefficient, which comes out here for these branching dynamics, or this is capital and birth and death processes and so on. I take it and put it into also the setting where we are, also PDEs, because they are not free PDEs. The drift has to do with the diffusion coefficient and so on. And then look at the Lie groups that are still available for this. And there is a beautiful feature. This is a paper with Mark Craddock. We can see that, and also in the book with John Bordeaux at Springer, Springer. What happens is you can, with pretty much just a constant also initial solution, put the prolongation of the Lie group, also the operator on it. And what comes out is suddenly the density, the probability density which we are looking at, and we get an explicit solution. This is also how in nature, and it's beautiful, how nature creates actually very simple, very simple is not correct, but reasonably simple and definitely tractable solution. And things we know, and they come up everywhere. So I have Bessel process, also Bessel functions, and all these things which come back to Euler macaroni constant, much more, and all these things, they come up. They are just there. Again, this is a nature. And this is a nature of, we are going here in like the logarithmic mode. If you would, it's just a comment, if it would be so in nature that the density, the solution of the PDEs would model everything that it's really independent, like independent particles, we would get the heat equation like in thermodynamics for these things. But it's not. Here's a feedback, here's a something conserved. So we have all these Wells particles that evolve independently, but there is a square root in this diffusion coefficient, so it sits in the PDE, and there is this kind of extra extra complexity, and you can see it in the Lie groups. Huh? And that's it. And in this world we are living here now, we are living in the world where the Lie groups are having these square roots, and which are then, we call it in mathematics accurately, okay, some say square root processes, Cox-Ingalls loss processes come from finance, or squared Bessel processes, a bit more general, but really fully general, they are so-called squared radial Ornstein-Uhlenbeck processes. But we know mathematically this beautiful, beautiful mathematics. They are very well studied, and we know a lot. There's self-similarity, there's additivity properties. There's also Mandelbrot self-similarity comes out of what I discussed here very naturally.
Thank you. There's a question at the back. No questions online. Okay.
Okay. Oh, thanks for the presentation. So you showed some fascinating results for a single person applying this EWI. So
Yes.
yes. So what actually would happen if everybody applies that? So what is the back reaction from the markets on this procedure?
So this is a very good question. As a first, we are very far from anything like that. Okay. But then I go back to the conservation laws. I have to go back and have to see what is happening then. What will happen is, or what I can imagine now, to quickly, without too deep thinking on your question, the pension funds, or here who's running the ETF and so on, will really go strongly on anything which is getting cheap, and on anything which is, and would sell everything what is getting high. So it's squeezing out, it's stabilizing the market. It's stabilizing the market dynamics. Yeah? And also the hedge, which is here, when you go for this zero coupon bond approximation, whenever the market crashes, it's not doing what many did just the COVID crash, pension funds get so worse, and what could be next? And then it's more. So selling, so they sold. And a few days later, it came up. Yeah? So they lost, they're out. The strategy says, you should buy more when it is going down, and exactly so much. Okay? And if you do it, you are there. So also, I'm not concerned about it. It will stabilize more the market, and maybe, that will be, I think, take some, let me call it now, energy or here information out. But then the market will be not so that it's all flat. No, there will be still all this there. And I'm not concerned, because this is the other point, and okay, there's more research necessary, and I'm not there, but my understanding is so. The buy and hold strategy of the MSCI World Index, okay, gives us something. And this is actually the natural growth of the market. Then we formulate this growth optimal portfolio of the stocks, so the EWI 163 you just mentioned. What are we doing there? We dynamically reallocate pretty much every day, or pay our 40 basis point transaction cost, but always when there's a very clear strategy, we buy low and we sell high. Okay? This creates a bit of demand, correct? But as it is. First,
Thanks so far, but I'm not quite sure whether you answered my question. So I understand that it can stabilize the market.
Yeah.
But if 8 billion people did that and applied that model, what would then be the benefit for an individual? So one element of those 8 billion people.
Look, also first, as I said, I'm not so concerned about it at the moment. But this is a question. And yes, I will look deeper into it, because I think in the conservation law, of course, energy will be conserved. And we will see where these dynamics and the feedback mechanism is. At the moment, I don't worry. We are pretty sure if, say, most of South Africans would just buy these ETFs, there will be these brokers will love this ETF fund because it will always be on the other side, whereas the other ones, and they're always the other ones, and you see it in the world, there will be a large group of investors who say, no, we continue as what we did. And it's good. This is good so. Yeah, it's good so. But I have not searched this question, investigated systematically this. What happens if this fund, this strategy is going further and further? However, it appears to me to build this EWI 163, you put work in, and this rewards you. And this is where energy is coming from, and which gets further and further. Some of it, I don't know, one has to go to numbers and see. But this is a long way, certainly after my lifetime.
Okay,
If
thank
there's
you.
Any question?
Thank you.
Are there further questions? No? Then let me maybe finish with something funny. You know, my original long-term plan was to drop dead on the golf course. And that's why I don't play golf. And I was planning to start when I'm 85. Yeah? But now I will do a little investments in your ETF and start playing golf when I'm 100.
Okay.
Yeah. So that's my new life plan. Yeah. So thank you very much, Professor Platen, for a wonderful talk. Thank you very much.
Thank you.
And according to plan, there should be some snacks and drinks outside. So please join us there. Get that as a little thank you. I want to give you a magazine that NITheCS produces and distributes in high schools. Yeah, so
Very
you have
good.
something
Thank
to
you.
read on the flight back to Australia.
I also show to my wife. She is interested in this. Thank you very much.